Good morning, good afternoon, good evening. Today, our lectures will be about one of the main common artificial lift system. It is will be about electrical submersible pumping system. We'll give some basic and some fundamentals about the system, how the system will work, and so on. The ESP, one of the common type of artificial lift, as I said, and it will, these lectures will cover, just some introduction about the system, what are the main components for the service and downhole. We'll give some hint about design and selection, due to sake of time, maybe we're not able to cover all the details of design and the other, like, equipment failure analysis or just troubleshootings and so on. What is an electric submersible pumping system? Electric submersible pumping system, it's considered one of the mechanical assist of artificial lift groups. Remember, in the first lectures, we said that we divide our artificial lift to two main categories, either formation pressures assist or mechanical assist. The ESP is one of the mechanical assist types artificial lift system. Also, when we are divided this artificial lift, we divide it to two, as I said, mechanical and gas or formation assist. Even the mechanicals, we have positive displacement and dynamic displacement. The ESP is among the dynamic displacement system bumps. The bump itself, it's a dynamic displacement bump of technique or system and so on. Then what is artificial lift? What is an electric submersible pump and so on? Electric submersible pump is a typical of artificial lift system. It's, as I said, it's a dynamic displacement. Then it is used a multi-stage centrifugal type of pumps, just to produce formation fluids, whatever water, oil with gas, two-phase flow, and so on, Mainly it's using a centrifugal force. It's dynamic, but, mainly is using what type of force just to give a dynamic energy to the fluid. It's through the centrifugal force. The ESP considered as the second most used artificial lift system worldwide. But if we start to say what are the main common artificial lift use at a volume, as a productions, as a volume of production, ESP come to the first, because usually ESP, it's used for high volume wells. Since it's used for high volume wells, even if the number of wells worldwide, it's less than the road lift system, but as a volume of production, a volume of fluids produced worldwide, the ESP come to the first. The first artificial lift can produce, it's produced the highest volume of produced oil and waters, from the wells and so on. ESP just in roughly, roughly, this is rough figures, it can be used to 15,000 or more, feet depths wells. It's one of the really the main common artificial lift for high volume. You can produce more than 60,000 barrels per day if the reservoir, if the well is capable to produce this one. The downhole equipment can be, it's not on all times, can be adapted, to high temperatures, but usually it's not preferred to use ESP for high temperature unless we are using a certain techniques to cooling the downhole equipment or motor. It's good, just can be good for corrosions. We using a special type of material. For gas, it's fair, but even now with a new technology for the downhole gas separators and the type of the pump configuration can be handled a good amount of gas and so on. It's for solid usually is not preferred if there is a sand and so on to produce this one, because it's usually working with a principle of centrifugal force, and the sands can create big problem for the pump and so on, For fluid gravity, it's not recommended for high viscous fluid and so on, and usually can be used for fluid up to 10 degree, but is not recommended, usually sometimes in use before 20 degree API, One of the challenge for this type of artificial lift, it's required usually a work over rigs in case they have a failure downhole because the pump is connecting to the tubing and the tubing string. In order to pull and run this tubing string, you required a rig, From the name, it's use an electric motor as the prime movers to drive the pump, For offshore, there is not a heavy equipment at the surface. It's an excellent for offshore can be used as a total system efficiency compared to the power used to the power generated or just useful power from the fluid lifted with a delta P. It can be ranging from 35 to 60 percentage, as a total system efficiency. It's come after the road lift system, the reciprocating road lift system and PCP. Usually have really some good advantage, for to use this type of artificial lift. It can be used high volume when you are coming to the volume production, when you start to select an artificial lift wells and you found your well productivity is high and it's required to lift a high volume. ECB, one of the first choice come to your, to your mind to use, this compared to what? Compared to the positive displacement type of artificial lift in the road lift system, the reciprocating and the positive displacement and so on, There is different size, different size for this type and of pumps and equipment downhole, motors and so on, different configurations for the pump itself and so on, It's not required heavy equipment or big tools or big part of equipment in the service. It's minor service equipment, We'll see later on, what the service equipment it's used. Even this type of artificial lift can be adapted to slim hole wells, you can run up to in casing, up to 4.5-inch casing with special design for sure, Also for deviated wells can be run with a special design and so on. But meanwhile, as I said before, all type of artificial lift, even if you have advantage, even you have a certain application, but meanwhile, each type have a certain limitation. When I start to select a type of artificial lift, after I said, okay, yes, this can be handle my wells, but what could be the limitation to use, For example, for the electric submersible pumping system, they required a source of high power, high voltage, because it's high horsepower motors run for a deep, certain depths of wells, there is it's far from the surface. They need power to transfer from surface to the pump. Will be a voltage drop, for across the cable used from the surface. For example, up to the pump sitting at 5,000, 6,000 feet, even 11,000, 12,000 feet. All that there is a pressure, there is a voltage drop. In order to compensate that, you have to use a high voltage source at the surface, the presence of power cable with the rod string, because the power cable usually is run outside the tubing, then it's alongside the tubing string, can be create some difficulties, while we are running or boning. We need more attention, more, more attention for the cable, not to scratch, not to, to have some damage of the cable during running and pulling, and you have to calculate very well what the clearance between the tubing and casing, not only the tubing itself, the coupling of the tubing. Because for an example, if we use 3.5-inch tubing, the coupling of this one is 4.5 inches. And if you run this in the casing, for example, 7-inch casing with a certain weight, the inside diameter will be about 6.27, 6.25. Then, and if you run with a cable 1 inch, then the total side of the cable plus the coupling will be 5.5 inches around, around this figure. And the casing, it's 6.25, then almost less than 1 inch, or just we can say around 1.5 inches, something like that. between casing and the cables, if you divided these to 50% on all sides, in the side of the tubing or the casing, then it's very small area. However, the temperature also consider one of the limitation for the cable, for the motor, because the motor itself, when it's running, is generated heat, and the motor usually requires some cooling. If there is no good cooling, the bottom hole temperature is high. This can affect on the motor's performance and the motor running life itself. It's also the capability, or just to match with a change in well productivity. It's not an easy, because this pump must be run within a certain range of production, certain range of flow rates. Flexibility of change that is not high like a rod lift system or some other artificial lift. This type of artificial lift, it's not an easy to repair as a field. For example, if you have failure in the pump with motor, something like that, and pull out of the well, it's not easy to repair, and usually is not repaired at the field. You have to send to the manufacturing outside of the field. This is a cost, and but the other type of artificial lift, gas lift valves, or just a rod lift system or PCB, you can repair at the field and rerun again on the well. Pulling and running of this type of artificial lift, it's costly because mainly it's required rig and downtimes for the well to pull and run the tubing and so on. And this is also always cost for operation. This type of artificial lift, or just what we call ESP or submersible, this type of pump, a centrifugal type of pump, can be used for the well. And also there is some type it's used as a service called horizontal pumping system. Same concept, but different motors and so on, but same concept of the pump itself, as centrifugal pumps and so on. What are the equipment, the ESP equipment? Let us to go for downhole equipment system component. What are the main components of that system? Let us to go to downhole. What are the downhole component, and what are the main component for this system, and so on. And surface component in meanwhile, the system component, downhole component. If we start, if you look to downhole, we have mainly the three-phase electric motors, which will feed the power to the pump and run the pump and so on. Plus, we have some what we call seal sections. The motor is electrical, and this motor have something to protect it from the fluid produced. Then we have what we call seal section or protectors. Meanwhile, we need to have a pump intake, some devices, to send the fluid or to feed the pump with the fluid. It's called the pump intake. And the pump itself, it's a pump usually is called multi-stage centrifugal pump, consisted of different stage and so on. Plus the electric cable, which is connecting the motor to the service power source and so on, and some optional equipment like sensors or like some other tools like Y tools and so on can be used down. Service equipment, we have what we call motor controllers, how to control the motors, how to control the power into the motor, how to monitoring the power, used by the motors and so on. Then we have motor controller. Since this type of motor used for electric submersible pumping system is required high volt, then we must have what we call a transformer as a surface in order to feed the pump with the required volt and so on. There is some device called J-box. I will show you later on when we go in details for the service equipment. What we mean is J-box is just, certain very small, simple, boxes, it's mainly for safety and for measurement, some use for safety and measurement for device, Variable speed drive can be used as an optional in case if they want to change the motor speed to match with the well productivity for different production and so on, plus the wellhead itself for the ESP. Let us to go piece by piece, and we have some information about how it's working, what's the main component for this part, and so on. As I said, the main part of the heart of the system is the downhole pumps for all type of artificial lift if I used. ECP downhole pumps, what are the downhole pumps? What are the main component of the downhole pumps? How these downhole pumps is working and running and so on, The electric submersible pump, as I mentioned previously, it is dynamic displacement pump. Dynamic displacement pump consists of different stage, more than one stage, more than one stage to produce the required fluid with a certain head, Then it is a dynamic displacement, multi-stage. The main principle of operation for this pump, it is a centrifugal type of pumps and so on, The pump is producing total dynamic head by what, by converting the fluids, the motor shaft is rotating. When the motor shaft is rotating the pump, the pump impeller, something called pump impellers, This shaft horsepower is provide velocity energy, because when it's rotating the fluid, that meanwhile, this horsepower is transfer some velocity to the fluid, and this fluid energy move the production fluids up to the tubing, by converting it to as a head and so on. Each centrifugal pumps have more than one stage. Each stage, as I said, producing a certain head of certain head for the fluid, Then each stage, it's stacked to each other, depend on how many stage I need, based on the design, based on the selection, and so on. Then the stage is stacked on a shaft, and this stage is compressed together all in a housing, and this what we call the subsurface ESP pump. Then this is just figure about how the pumps looks like from inside. If you look here, it's have different stage. For example, at 1, 2, 3, 4, 5. Depend, as I said, about how much head I need to lift this pump to the surface and so on. And this is what we call pump stage. Each one of these is a stage. This is pump stage. Pump stage consists of what? What's mean of pump stage? How it looks like from inside these pump stages. The pump stage have three main components. First, if we take one of these stage and see what's the main component of that stage. First one is what you call a rotating impeller. This is the only part inside the pump is rotate. Is a rotating impeller, called impeller. Second part, it's called stationary diffuser. Then each stage of the pump have two main components, or mainly it's three, but the main component is two. One rotating and one stationary. The rotating is impellers, the stationary is a diffuser. Between the two, just it is what we call thrust washer, some washer just to fix it and to hold these two for each other. The type of the geometry of the stage control the volume. The geometry of the stage itself is controls the volume based on the volume and the size of the stage itself. Depend on how much volume I need to lift and so on. And also the fluids and the fluid going to this stage, it's lifted up depend on number of stage, how many number of stage I have to use. Then the type of geometry of the stage controls the volume of the fluid that can be go through. The number of the stage determine the total dynamic head generated. How much dynamic head I have to generate to lift the fluid from the pump up to the surface. For the type of stage, there is different type, different geometry currently rare, something called radial flow, maxed flow, axial flow, depend on how it is, handle the float. When the float going to the stage, how it's handled. Then the stage configuration from inside, is different, have different stage, depend on the situation, what we have in the well and the float types, and so on. Let us to go a little bit deeper about, impellers and diffuser, because this is a very important part. If I understand these parts, I will understand the system, how it's running, how to troubleshooting, how to control, and so on. As I said, the pump have different stage. Each stage have impeller and diffuser and washers. This is, this is the shape of the impellers. And this cutway, the bottom one is a cutway inside. This is the impeller of the stage of the pump. The impeller usually is fixed on the shaft. There is a shaft in the middle of the pump, and this impeller keyed on the shaft, then fixed on the shaft. When the shaft is rotated, the impeller is rotated with the shaft on it. Then the impeller is keyed into the shaft and rotate about the center, about the axles of that shaft, and so on. When the fluid enters the impeller through the bottom eyes, this eye near to the shaft, and exit from outside, to this impeller, like this, If you look to the red arrow, impeller is a fluid going in this way, and then get the velocity energy by rotating the shaft, then rotating the impeller. When the impeller is rotating, giving a velocity to the fluid, and due to the centrifugal forces going outside from the center to the out with a certain head, with a certain power, certain energy, which can be converted to the head after that, and so on, Then the impeller takes the fluid and import what we call kinetic energy as a velocity, to that, Then the fluid go out of the impeller with a certain velocity, with a certain kinetic energy. Then how this is velocity, it's transferred to the head, After that, if we have a diffusers, the diffuser is connecting outside of, or just outside of the impellers, Then when the fluids come out of the impellers is hit the wall of the diffuser. When he hit the wall of the diffuser, he found himself, only going out because the bottom of the diffuser is closed, but going out with a certain the kinematic energy, with a certain energy which is converting like to the head to the surface. Then the diffuser does not rotate. The only rotate here, is the impeller. It's turns the fluid up into the next impellers, Then when the fluid go out, it's only the main function here is turns the fluid come from the impeller to the next impellers, above it. Then the fluids like this, come from the diffusers so from the impeller to the diffuser, and the diffuser transfer it up to, in the vertical movement to the next one, and so on, next one and next one, until we reach to the last one, and then going to the tubing with accumulated heads, built by each stage going through, is a fluid going through it. This is, what we call, the diffusers and the impellers. This is the two main component of the pump stage. Then the diffuser convert here the kinetic energy, the velocity gained by the fluid from the rotation of the impellers produced by the impeller into potential energy to the head, and so on. Then this is one stage consisting, as I said, from diffusers and impellers. The diffuser and impellers will connecting like this. One of them is rotated is the impellers, the top one, this top one, and one is not rotated is the diffusers. This is just how it looks like. The fluid when we enter to this fluids from diffuser to the impeller to diffuser to impeller, and so on until it's reached to, to the tubing, and so on. This just, gives me some figure just about how the impeller and diffuser working together, how they are provide heads and fluids, from one stage to the other, to the second stage, and so on. After that, come to the downhole intake, in order for the flow to enter to the pump, because the pump is closed from the housing outside, then it should be something, like a manifold, like the intake, like something, to feed the pump with the fluid, To feed the pump with the fluid, there is a certain equipment, certain part of equipment called intake. The intake have some ported, from side of this one, and this fluid, when we going to the intake, is going to the from intake to the pump. Then the intake is a section attached to one, to the base of the subsurface pump. What are the main function of that? Is to provide the entrance to the fluid. How the fluid will enter to the pump. The main function of that is to provide entrance of the fluids to the pump, This intake in general, since it's provide entrance to the pump, it can be one of two configurations, Either can be standard ports, just only opens hole for the fluid to pass from the annulus of the well, from the downhole of the well to the pump, or if I can use it as a gas separators. Because if there is a gas and so on, why I not use this as a gas separator to make two functions? The first function is to separate the gas, and meanwhile to allow the fluids to enter to the pump, And sometimes, it can be have some screen and so on outside. That's in order to help as a sand separation. It's not common use, but it can be, and so on. Then how it looks, the intake, if the intake is downhole gas separators, how it looks from inside, water can be from inside. Since the pump is rotating and the motor is supply rotation, why you not use this as a as advantage to my fluids, and rotate the fluids before to enter the pump, and due to different in gravity between oil or just between liquid and gas, then they are separated, due to a centrifugal forces generated or just, provide to this flow. Then gas separators, it separates the free gas, just we must have separated the free gas before entering to the pump. Because as I mentioned in the first lecture, that the gas is reducing the pump volumetric efficiency. Is there is different type of this one? Yes. There is some types, it's called static, but it's not common used for the ESP, because ESP is rotating and so on, And the main one used for the ESP pump is the gas separators. And there is a rule of thumb, when you start to design the ESP pumps, depend on type of pumps, type of stage, and so on. There is a free gas as a pump intake within a certain number, a certain value, then you have to use the downhole gas separator. You don't need to design or operate a gas separator under the backer. If there is a backer, and sometimes, it's not always used, and there is a backer above the pumps and so on, then you don't need to have this downhole gas separator. The well is backerless, or just, there's a certain type of configuration of well completion, but there is a certain technique of downhole gas, well completions, and so on. Important part also for the downhole component is called protectors, and some people named it as a seal or protector. What is the seal and what are protectors? Remember, we have downhole pumps, and below the pump we have intake, and this pump you have to run with motors. If I connect things in like what I have in these pictures, the motor to the intake of the pump immediately like this, what will happen in this case? The fluids will enter into the pump. For sure, will go and to enter to the motor, and these electric motors can be damaged. The motor can be you know, burned the motors and so on, you know. Then in this case, I will be not, it's not, you know, it's not common use, or just is not used at all, you know, to connect the motor direct to the intake of the pump. This is not good, or just we cannot do that, because by this way it will damage the motor immediately, you know, when we run. What we'll do in order to protect the motor from the fluid entering to the pump, in order to protect the motor from the fluid entering to the pump, they have to use a separation between the motors and the pump intake called protector or separators. Then protector or separators is connected between the motors and the pump intake. It's connecting just between these. This is a red one, you know, here just between the intake and the pump, the motor. What are this intake? What the function? It's only just protect the motor from the produced fluid, or have some other function, since they are using a piece of equipment. Why I just, you know, not get some more benefit from this piece of equipment. Then the seal section, as I said before, is a protector. It's called protector, you know. And the main purpose, you have different function, different, you know, function for this one. One of the main important function for this motor, or for this seal section, is isolated, as I said, you know, isolated, and protect the motor from the oil fluid. This is one of the main function, one of the primary function for this one. Second, since this motor is electric motor, there is an oil inside, and this electric motor, you know, used for insulation, cooling, and a lot of things for the motor it's used. Since there is an oil, and the motor is this oil is in enclosed cylinders, you know, the motor is in cylinder, enclosed cylinder, and the bottom oil temperature can be changed, you know, and the motor itself is generated temperature. Then this oil can be expanded. If the oil expanded in a closed section, what will have? This generated more high pressure. This can be, you know, damage, can be damage the motor. Then this seal section can provide, you know, expansion of motor oil. If the motor oil expanded, it can go to the seal. There is a certain room in the seal can be absorbed the expansion of the oil, motor oil, you know. Meanwhile, also, it's equalizing the pressures between, you know, the well pour and the oil inside the motors and so on, because due to different pressure, differently, different temperature, the pressure can be, you know, high and low, and so on, you know. Also absorb shaft thrust, you know, if there is some vibration in the pump, and so on, you know, it's absorbed before it's reached to the motor and so on. Meanwhile, also is transfer the torque generated, the rotation generated from the motor to the pump. This is just some of the main advantage, main function of using a seal section or protectors between the motors and the pump intake. There's a different type. You know, it's not the time to talk about all this type, you know, because according to manufacturing, there is different type. Each type have a certain advantage and limitation based on the motor size, motor horsepower, the motor configuration, pump configurations, downhole conditions, and so on, you know. In the market, there is different type. If you Google about this type, you can have some pictures, you know, or some cutaway about how it looks like from inside, you know. All this is, as I show here, there is three main type, just can common used worldwide, and so on. Come down to the one of the main important parts, you know, I need to, you know, to run in a very good way in order to avoid damage of it, and so on. It is a motor. Then the motor, what is the motor of the ESP? And what the configuration of this motor, and so on. The motor of ESP is three-phase motor. Generally common used called induction motor. Even if now on the market there's different types of motors, but in general, the main common used worldwide, you found, you know, in more than 85 or 90% of the world of the well motor type is induction motor, you know. It's filled with oil for lubrication, cooling, insulation, and so on, you know. And the ESP motor, it's connecting to the bottom of the seal by bolting, It's not threaded, by bolting by here flange in the bottom of the seal and flange in the bottom of the motor and bolted to each other, Mainly the motor is converted the electric powers feeded by the cable to rotate to do us to convert it to rotation, which is rotated the pump through a series of shafted from the motor up to the pump bus from seal, intake, and so on, The common ESP motor are built based on different, voltage, In the market, there is different volt. You can find motor running in, for example, in 460 volt, low, very low volt, and you can find motor even run up to 5,000 volt motor, at different hertz, You can find 50 hertz, 60 hertz, or if you use a variable speed drive, you can control the hertz going to the motors and so on, These motors also, if I need more horsepower or more motor and one motor is not enough at the horsepower due to size, due to some downhole restriction and so, it can be used tandems, it can be used two motors together and so on to produce the required. The lower pictures, give some cutaway inside the motor, how it looks like and so on. And this is one of the main important bump of the pumps of the ESP system and so on. Currently in the market, there is different type of also of motor, the manufacturing and so introduce another type of motor called permanent magnet motor. I said the main common type of motor is an induction motors, but currently also there is another type called permanent magnet motors, is with a different technique of how the motor is running and what are the function and so on, The motor, it's a very important part. And the motor, as I said, is generated heat, and the motor requires the cooling, in order to have more good efficiency, good running life, and so on, Then the motor operating temperatures usually really is a very important. And what are determines the temperature around the motor and how to keep the motor running in a good environmental of temperature, It's determines the motor control or motor operating temperature. Usually there is 5 parameters. It's just determine temperature. What are the temperature at the motor depths? Is the flow temperature at the motor depths around the flow? It's around the motor, what its temperatures and so on, Second, how the motor is loaded. Is the motor running with each from each maximum load? Sorry for that. Then we said, there is.
So Mohammed, the sharing stopped.
Okay, I will do it again. Sure, I'll do it.
The last slide from beginning will be better.
Okay, sure. I will reopen it again,
Okay. Now we see it.
Okay, good. Okay, let me back, just for the slide before this one. We said about, the motors and motor type, and currently in the markets, there is different type of motors. It's what we call permanent magnet motor and induction motors and so on. Even the both type of motor, we have to control the bottom hole temperature around the motor, because the motor operating temperatures is one of the main critical factor for ESP operation, for ESP performance, motor performance, and so on, This is factors, the main important factors or the temperatures at the motor depths. One of the main factors of temperature is the well pore temperature. How much temperatures around the motor itself, at the motor depths. Second, how much you are loaded your motors, Do you running the motor near to its maximum load or 50%? When we run the motor at high load, is generated more temperatures, more temperature generated required more cooling and so on. Then this required to do some what we call some cooling for the motor. In order to do a cooling for the motor, then the fluid around the motor must be passed around the motor going to the intake with a certain velocity. Then fluid velocity passed to the motor. What are these velocity? How much is this velocity? When the velocity is increased, is cooling more, is generating more cooling, or just transfer more heat from around the motor to above, just absorb some heat and so on. This is a fluid rate just pass to the motors and so on. What else, It's cooling properties of the well fluid itself. If this well fluid is water, is gas, is oil, water was gas, water was oil. What is the cooling tendency? It's oil only and or water only and so on. This is just some of the factors plus at the end the power quality. What is the power going to the motor? Is there a good quality? It's stable powers, for the volt, for the hertz, and so on, or fluctuated, is making the motor, just to generate more heat, We usually like it's balancing, the power is going balancing because the motor is three-phase motor, and there is three phase, there is three conductors, and the power going to each conductors is almost the same as the volt and so on, or just, it's unbalanced, All that's affecting on the motor temperature. Then one of the main factors I have to consider when I operating the ESP is the temperature around the motors. The motor itself is generated temperature. Then I have to cool this motor. In order to cool this motor, I have to consider all these 5 factors, what I mentioned now, Then all of the above factors determine if and when a motor will be overheated during operation. I have to avoid that. I have, to avoid the motor to be overheated. When the motor is running in the good condition, good cooling systems, in the running life, the performance will be in a very good, records and so on. Above that, or just one of them, another parts downhole is the motor cables. The motor cable it's carrying the power, carrying the currents from the motor controller at the surface to the downhole to the motor down in the well. This is the main function of the cable. But in order for this cable to transfer the power from surface to the motor, this cable should be suitable for that power which will be transferred. Suitable based on what? Based on the power requirement to run this motor. What is the motor horsepower? What is the voltage required? What is the voltage required at the motor itself, and so on. This usually in the market, there is two configurations, let us to say two configurations of the cables, ESP cables. Can be either flat or just rounded, like, these two pictures, and give me the flat one and the rounded one, Both can be used, it's without any problem, but, usually one of them, have some advantage over the other, but both of them do the same function and so on. Not only that, the motor, even it's flat or it's rounded motors, can be found in different shape, different configuration, different sizes, and different materials and so on, Usually the size of the motors, the size of the cable depend on how much, the size of the conductor from inside, And the size of the ESP is just, categorized as size 1, size 2, size 4, or size 6. Size 1 is the biggest size of the motor. The size of the conductor is highest than size 2, size 4, size 6. And when the size is increased, that's mean it can be transfer more voltage without, with less voltage drop, and transfer more powers and so on. What type of cable I have to use in general, not only the downhole cable. I have also surface cable, wellhead cable, through cable, main power cable in the downhole, and there is a special cable at the bottom hole assembly, starting from the pump up to the motor, called motor lead cables, and there is connecting motor connecting cable connecting at the surface called boot heads and so on. Even if the cable itself, we have to protect it, because this run in the oil and running in the fluids, can be oil, water, gas, oil and gas, environment, and so on. Then this cable, we have to protect it. And the cable of the ESP consists of different part, different part, like, conductors. The conductor can be mainly from coppers and so on. And then we have some protections around this motor. As I mentioned before, we have different size of motor. If you look to the table here, is there is have size 1, size 2, size 4, size 6, and this gives you what this size in millimeters, and what is the ampere capacity ampere can be holding by that one. I said size 1 is the biggest size of this type of motor, It can hold up to 110, amp and more sometimes, depend on the cable size or cable types or conductor types and so on. At the, at the motor itself, how we connecting this cable to the motor? There is what we call motor lead cable. The motor lead cable, due to that, the limited clearance between the ESP system component motors and all the bottom hole assembly component, and there's small clearance or between this assembly and the well casing, special cable, can be extended downhole around this bottom hole assembly and is using. The motor lead cables, is a special power cable that's extended, this is a motor lead cable extended, past the bumps and past all the bottom hole assembly, It's just, use a special connection at the two connected, so on,
Dr. Ghareeb, there is no voice. So Dr. Ghareeb will join quickly. He get disconnected. Dr. Ghareeb will join within 1 minute. 1 minute, he will be with us. Dr. Mohammed, now we have you. So please share your presentation. Dr. Mohammed, now I see you twice. So you connected maybe from two computers or something. Dr. Mohammed is trying to reconnect again, so just 1 minute, he will be with us. Dr. Mohammed, now we see the presentation.
Okay, okay. Sorry for what happened, you know. Yeah.
No problem. I will cut all of that from the video, so don't worry.
Okay. We stopped in this slide before, you know. We said about the motor, the cable, downhole cable.
You can start the slide from beginning. It will be better.
Okay, sure. Yes. We stopped at this slide, you know. We said, you know, the cable connecting the surface power to the motor, we have to fix it with the tubing from outside of the tubing, you know. There is different way to fix it, you know. Usually cable bands, you know, like the one in the middle, you know. This is the main common one is used to fix it. Just fix the cable with the tubing itself from outside, you know. One band, you know, usually they are using either one band each 15 feet or just maybe could be each 10 feet, you know, depend on, you know, the motor size, sorry, the cable size, the load and so on, you know. Cable bands also, you know, can be used to strip the motor flat cable downhole even, you know. The main important function of this one to fix it, the cables or just to support the cables with the tubing itself. As a coupling or if there is a deviation, there is a special band used like the one on the right and the one in the left and so on, you know. This is the main just part of the cable band, you know. Back again to the surface equipment, as we said, the surface cable, you know, usually need to connect what? To connect the switchboard to transformer to junction box, all what we are using in the surface, it's this what we are called a surface cable and so on. What are the surface component for the ESP? This is just a general layout about the surface component of the ESP. If we can starting from the wellhead of the ESP is just a very simple wellhead, is a Christmas tree. This is the main part of that. Plus, there is a special what we call tubing head spools with a certain hole, certain connection to allow the cable to feed to pass from it from the surface to the well with a certain connection, certain techniques or certain parts. It's used for this one. This is what we call the wellheads for the ESP, especially, for the tubing head spool and the part at the wellhead. This you must have some hole at a certain configuration like this one to allow the cable to pass from surface to down hole. Meanwhile, isolated, around this cable to prevent the gas or just any fluids to come out from this area around the cable. There is depend on how much is a well pressure rating. We have a certain wellhead for low pressure wells and another wellheads for high pressures wells. Look to the difference between the top one and the bottom one. The top one just only the cable with bus and bus like this. Top one we use a special connection, upper big or lower big what we called, with a certain seal because it's high pressure. You have to seal, this is against the oil pressures, especially the gas, because in the casing, the annulus, will be a gas. This is a tubing and this is the annulus, where the cable is going to the annulus and connecting the annulus, and safety here is a very main important, how the cable will connecting at the surface wellhead, at the surface wellhead, and how it's passed and to the tube, to the well inside, with with a certain technique or certain equipment, certain wellhead using for this one. Second part, it's what we call, remember, I said I will go through this one, is a J box or junction box, It's a very simple box, just used for a certain purpose, What's this junction box? If you look to that from inside this junction box is connecting the cable come from the surface motor controller and transformer and this one to the cable going to the well side. Then we have to have a separations here, It's not recommended to have the cable come from transformer or to motor controller direct to the well. Why? First of all, the cable going to the well, going in the annulus, and the annulus there is some gas and so on, The gas can have a tendency sometimes, to pass through the cable, because cable, you're not sure that it will sealed or so or something like that, Then the junction box will surface, as a vent box. If there is a gas pass or just venting through or pass through the cable coming from the well, this junction box should be vented the gas to the atmosphere. It's a very small amount. You cannot feel, you cannot see, but it's dangerous of the gas to allow the gas to pass with the cable to the control panels or to the other parts in the surface can have some spark and can have explosion. It's allow for any gas to vent to atmosphere that this gas before maybe it's migrated with a cable before going to the surface electrical connection or electrical equipment at the surface. Meanwhile, also it's easy for us to measure, if there is some problem downhole or I want to measure the cable powers, how the power is going to the well, what the power quality going to the well. It's just, provide easy accessible to the point for electric checking. I can check from this point and so on. This is just, how it looks like from inside. This is what you call junction box. Plus we have transformers. These motors is running with a high volt, at high volt. I must have a transformer, to feed the motor with the right volt. Meanwhile, taking into consideration the volt drop across the cable from surface up to the reach to the motors, then I have to feed the wells or the motor at the surface with the required volt. The volt required to run the motor plus the volt drops across the cable from the surface to the bottom of the motor. Then transformer system is used mainly to convert the inlet volt to the required volt, and you have two types of this transformer. If the volt coming to the well sides, it's low volt and I have to feed the motors with high volt, it's called step up transformer. Then this transformer take volt from low value to high value. If sometimes the volt come to high from the grade or something like that, it's high volt, and I need to, reduce this volt, is called step down transformer. It's just depend on what volt I have to run my motor downhole and so on. Then transformer selection is based on different parameter what I have. First of all, what is the power rating for the motors and for the conditions, the equipment what I have to use, what is the primary volt, what is the secondary volt. Primary volt is the volt in, what is the volt should be the volt out, how to arrange changing the volt across the transformer, what we call motor tap arrangements and so on. The other part is called motor controllers or just control system or variable speed with the control system and so on. The control system, it's a motor controller or control system is available, really, it's available in different configuration and different technology and different techniques of use, either can be a switchboard, this is what we call fixed speed switchboard. When I run, I run with a fixed speed, fixed hertz, just it's only used for on and off switch. It's on and off switch plus monitoring, it's provide protection to the cable and the cable motors and so on, and monitoring. Protection mean in case volt drop or just volt increased or something happen, it can be happening on and off or just shut down or so on, It also can be a fixed speed, but soft start, soft starter sometimes if I have a big motors and so on downhole and required very high starting current starting motor, this can be allows the motor to run smoothly and so on, or can be a variable speed, variable speed, yes, it's connecting to a certain connection or certain techniques, to change the speed going to the motors, then I can have flexibility to run the motor at different hertz, different speed, and so on. This is what we call the motor control system. Plus, we have additional downhole accessories and downhole parts, like pressure, downhole pressure and temperature sensor, vibration sensors. We have downhole backers. We have what we call Y tools, different parts, check valves and drain valves. All this, depend on your design, what's the required and how. This is, the system of Y tools, how it looks like, it's not using all the well, but you can use. The Y tool provide access to the well bore with the ESP downhole, When you have the ESP downhole, you will not able to pass below the ESP if the ESP connecting direct to the bottom of the tubing. You cannot pass through it. But with this configuration, it looks like in this picture, you have Y tools, Y tools is allow, to connect the bottom hole assembly in one parts, and the other parts, just will be free out downhole, which is allow you just, to run what you call like a production logging, coil tubing, whatever you need to run downhole the well to access the perforations and so on, This is just a summary about, summarize for you what's the ESP component, summary for pump, for intake, motor, cable, downhole sensor and so on, controllers and service equipment and so on. This is just a very brief about the system component, surface and downhole. How is the design? How we design? How to select the system? How to select the downhole pumps and the pump configurations and the other parts, I will not go in details for this one, but however, I'll give you some hints about that, Since this pump is a centrifugal pumps and so on, then will be what we call for each pump will be a performance curve related to the pump itself, The performance curve for ESP centrifugal pump are normally showing, what? Head against floats. Each centrifugal pump have this performance curve. performance curve, what we call this pump, how much head is generated against flow rates. Usually the performance curve, it's, for one stage, usually you will find the performance curve for each pump for one stage, and then you can generate it one performance curve based on your number of stage, how you are using for this well, Then this is the performance curve, it's flow versus head in either whatever, use meter, use feet, whatever units you are using, and so on. Then this head, that's mean how much head each stage is lifted the well, Head, that mean fluid lifted to the well, and the head is function of the fluid types and a lot of other parts we'll see later on, and so on. Then the head for ESP, it's the height to which the pump will lift fluids. This pump lift fluid 10 feet, 20 feet, 1,000 feet, 2,000 feet, whatever. Based on that's what we call, this is a head, and so on. For ESP, since it's a centrifugal pump and depend on, centrifugal force and convert, the fluid from velocity to the head and so on, there is some general concept here you have to put in mind, is a centrifugal pump produce constant head regardless of the fluid being pumping, because this is a function of the centrifugal force and velocity given and then transferred this to the head. It will be lifted the fluid to the same heads, for the same flow rate. If we have same flow rate, then there was different fluid will be with the same heads, and so on, with the same speed, and so this is a performance curve of the pump. And let us, just to assume how we use this performance curve and so on, assume they have 1,000 feet well to lifted, fluid at 600 barrel per day. For one stage, if how much fluid it's will lifted, based on this type of stage configuration, assumed at 600 feet, as I said, this stage, one stage from this certain type of pump is able to lift around 40 feet. Then in order to lift fluid to 1,000 feet, how many stage I need from this type of stage? In this case, I divided 40 because each stage is generated for me 40 feet. In order to lift 1,000 feet, then the number of stage in this case will be how much? The head for stage will be 40, then the required number of stage, it will be 1,000 feet divided by the head per stage. Then in order to lift the fluid 1,000 feet, I required 25 stage minimum for this well to lift fluids with 1,000 feet to the surface with this type of stage, with this velocity, with a certain velocity, and so on. One of the main important things you have to be considered when you are running your pumps, when you are running your ESP, about how the stage is running itself. You have to run the stage in a very good conditions in order, to have a longer running life, because this is centrifugal force, and the stage, one of them, impeller is rotating, the diffuser is not rotating, and then I have to have what? These two parts should be rotating smoothly around each other, without contacting each other, in order not to erode it or to eat it each other, Then the fluid here, this is a picture of the impellers and the stage, When I'm producing fluid through this one, the fluid in the normal cases, the fluid creating a pressure on the upper parts of one of the impeller's shroud here, because it's lifting fluid, it's going fluid here, and the fluid going to the other one is lifting by this stage of this one. Then the fluid creating pressure on the upper and also lower part of the sea, because fluid going up like this. But the upper part is have a bigger area than the lower part. The fluid creating pressure on the upper part and lower part, as I said, in the impeller shrouded, the surface of the impeller have large cross-section area on the upper shrouded. Large cross-section area that's more force in the top than from the bottom, and so on. This cause what, if pressure is increased more and more, then this is impeller will cause impeller to force to go down. Force to go down, that's mean this is positive moving, go down, is creating something what we call down thrust. Remember I said, the pump stage have three main components, impeller or diffuser and thrust washer between the two. Down thrust, that means this is forced on the washer, forced on the thrust and self. This will be a metal to metal friction between two if it's going, you see how it's moving down here, with the loads, if the load is increased and so on. This causes the move, as I said, the impeller to move down. In the other part, if the fluids going from bottom to the up is very high, what you have, this high fluid moving down will push the impellers to go up. This causes the impeller to move up, when at a certain point when the fluid it will be higher than it's normal to produce. Going up, what we have this. In this case, we have up thrust bearings. This will be contacting to the upper washers, to the upper diffuser, and this is what we cause up thrust problem for this one. For that reason, why I said this two times, for that reason, when we run the ESP, I have to run not up thrust, not down thrust. The impeller and the diffuser should be run a floating, between each other. Not up thrust, the lower one is contacting to the upper one, or not down thrust, the upper is contacting to the down one. For that reason, for each ESP performance curve, you will find at the middle a certain range of called recommended production range or recommended operating range for ESP. Recommended operating range, that means you have the impellers and diffuser, it will be in free floating impeller. Free floating impeller is not contacting the top or not contacting the bottom. In your design, you have to run within this operating range, operating condition, in order to have more running life. If you found your system is going right or down, you have to correct this problem, a down thrust or up thrust. If the fluid, you start to produce less fluids, that's more high volume, because according to the performance curve, less fluids, high lift, less fluid, high lift, high dynamic lift, the pump lift. Then the impeller is going down, go down thrust. More fluids, you have more fluids, then the head will be less head, then but fluid going from down, it's high, then you have up thrust and so on. This is just, very brief about this one. We'll not go in details for this. Pump selection, within the pump, how to select the pump. Based on the desired production, first of all, you have to select the best configurations of the pump stage and so on. Plus, you need to determine what is the bottom hole pressure, what is from the IPR. Bottom hole pressure is the intake pressure. Difference between intake and discharge pressure. This is the pressure of the pump you have to generate. You have to calculate the minimum depths while I have to run this pump and so on. This is just a main concept about, how to select the pump. You have to determine not only after flow rates and the bottom hole flow pressures calculated, then you have to determine where the pump you are setting. Then you need to calculate the pump intake pressure. After that, you need to calculate how much dynamic head this pump required to lift to the surface to overcome the hydrostatic head, the wellhead pressure, and the pressure loss in the tubing and in the system, and so on. In this case, also you have to select the pump at the recommended range, and usually you started from the highest efficiency at the middle of the recommended operating range. After you are calculating the number of stage, or calculating the head per stage for each stage, and you calculating your total dynamic head, then you need to calculate to determine how many stage I required to run for this pump in order to lift my float and overcome, all the friction loss and all the dynamic head. After that, you need to calculate horsepower required. Horsepower for the motor required to run itself. Horsepower for the motor required to run this pump, to require to rotate the intake, required to rotate the seal, and so on. The total horsepower and the cable size and the voltage drop in the cable and so on. Then this is just an example for in front view about the performance curve of the ESP. Usually the performance curve of the ESP have three curves, One of them, the main curve is the blue one. Here, it is the head per stage. The head per stage, and this head per stage is a function of the type of stage, function of the speed of this stage, and so on, Plus, you have is what you call another curve. This is the green one. It is the pump efficiency. This pump, when is running at this rate, what is the pump efficiency? And at that rate, what is the pumping efficiency? Plus, we have the red one. It is horsepower, brake horsepower. The horsepower required to run this pump, the horsepower for this pump in order to lift fluid with this pump for that. This is for one stage, huh? Remember, this curve for one stage, this horsepower for one stage, and so on. Plus, for each curve, as I said, for ESP, you have in the middle a certain range. This is the yellow one, what you call operating range, recommended operating range. When you start to design or selecting the pump or selecting the right stage for this pump, selecting the stage which can give you the right production, and meanwhile at the middle, at the top, of efficiency, at the middle of the recommended range, usually in this case. Then you have to calculate the head per stage, the pump efficiency, the brake horsepower, and also you have to see what is the best efficiency of the production at the best efficiency here, Each curve, it's characterized with what? With pump type or just stage configuration, with the speed, and this speed is running at what hertz, and so on. For example, this one is this single stage performance curve. This is for one stage at 3,500 revolution per minute, RPM, for tested for water with specific gravity 1 at 60 hertz. Usually, this is just how to read the performance curve. If I wanted to produce this well at 4,000 barrels per day, then this stage, generated 42 feet at the head for this head for this stage. That's mean for this type of pump, if I use this type of stage, then each stage, if I wanted to produce 40,000 barrels per day, this is lifting 42 feet. Okay, at that rate, what will be the horsepower? What will be the pump efficiency? At that rate, for each one of these stage is required about 1.8 horsepower. Then each stage will produce for me 42 feet. Meanwhile, it's required 1.8 horsepower. This pump is running at around 70% efficiency, as a pump efficiency, mechanical efficiency, and so on. For example, this well like that, in order to calculate to see how many stages are required, what's mean if each stage generate 42 feet, then how to calculate the number of stages. This is just looks like I have the well. If I have the well like this, with a delta B from reservoir up to, and we said that one of the main important things to calculate is the total dynamic head. How to calculate the total dynamic head? This pump should be generated in order to produce the required flow rates from bottom to the surface and transfer from surface to the inlet of the separators or just a facility, whatever you have. What are the main components of the total dynamic head this pump should be generated or should be overcome, and so on, this is just a schematic of the wells, producing wells, what is producing. Really, it will start with a flow. If you are decreasing the bottom of the pressure, flow will come from the formation to the bottom of the well with a pressure. It's equivalent according to the well productivity to the bottom hole flowing pressure. And this flow should be go up and to the pump depths, to the pump intake, and enter to the pump through the intake. And the pressure as this intake called the pressure intake, the pump intake pressures, and so on. After that, we need just this pump to generate pressure to lift fluids to the surface with a certain well head pressure, and meanwhile overcomes the hydrostatic head of the pressure inside the tubing and friction loss plus the friction loss. And also, this is just a very simple, schematic about how the flows go. Plus, this pump should be generated a certain wellhead pressure. This wellhead pressure, it's depend on, how far from the facility, what's the production, pressure loss on the surface, and so on. However, this pump should be generated. This pressure is capable to transfer the fluids from the well to the surface facility. What that mean? That means the total dynamic head is equal for, first of all, the first item, including in total dynamic head, should be equal the fluids from, from the fluid level, the dynamic, because according to the bottom hole flow pressure and the production, this will be a fluid go up, up to a certain level inside the well, and from this fluid inside the pump, then the pressure inside here, if there is no flow, will be equalizing, until these depths. However, the total dynamic head is equivalent to what? To the net vertical lift. Net vertical lift is the net lift from the fluid level up to the surface. We have to consider the casing pressure here. The casing pressure also, it's supporting us, and you have to consider this in our calculation. Plus what, plus, the friction loss. In order this flow to flow inside the tubing, this will be a friction loss depending on the tubing size, the roughness of the inside diameter of the tubing, the flow rates, I produce the type of the flow, viscosity, and so on, Then I have also to calculate the total pressure loss. Then I have the net vertical lift plus the pressure loss, plus what else then? Plus the wellhead pressures. Then another items here is the wellhead pressure, this item number 3. Then the total dynamic head should be, this net lift vertical plus pressure loss plus the wellhead pressures. Based on that, I have to calculate, how many number of stages required to lift that total dynamic head, to produce this total dynamic head, depend on, as I said, the stage configuration and the performance of this stage and so on. Then the number of stage here, it's required for the pump to overcome all that, the total dynamic head is equal what? Equal each one of these stage, how much the total dynamic head it can be produced. Remember the pump performance curve we are presented, in the previous slides. Here, for each one stage, how much it's generated as a total dynamic head. Based on the total dynamic head I have, plus the head per stage, then I can calculate it, what is the number of stage, the minimum number of stage I can be used for this type of well, or just to produce these wells and so on. Let us have a very simple example, just assumed I wanted to produce 3,600 barrels per day with a total dynamic head calculated based on the previous slides, it's 4,590 feet, and depend on this 3,600 barrel per days and the condition, I will gonna to select the suitable stage, the suitable pump to produce this fluid. And based for each pump, there is a performance curve, looks like the one in the screen here, This performance curve, as I mentioned before, for a single stage, at a certain RPM, that's mean a certain hertz, for example, 50, 60, whatever based on manufacturing, based on you, and it's based on specific gravity of water one. We said each pump performance curve have three curves. One is represent the head stage or head capacity. The second one presented, the pump efficiency, and after that, it's brake horsepower. Based on this one, why we select this one, we said that we need to select the pump which can be produce my desired production within the operating range, and it's recommended, to be at least, nearest to the peak efficiency of the pump. Here, for the green curve here, if you look, this is the peak efficiency. If you go down the peak efficiency, yes, this 3,600 barrel per day, and you need to take into consideration will be a constant flow, or with time this well is depleted, or what going on, we're working, within operating range for the life of the well, or just for a certain period of the well. Do I need to start with the best efficiency, or just try it, but within the operating range, right to the best efficiency, because in case the well start to be depleted, I will be still in the operating range, However, based on that example, if I want to produce 3,600 barrel per day, then I came at 3,600 barrel per day, and I go up until I reach, to the head capacity curve, The head capacity curve, I have to, measure, based from the curve, what is the head per stage this pump can produce in order to produce 3,600 barrel per day. If you look here, it's around 45 feet. Then each stage of this pump, it can be lifted 45 feet. Then how many the number of stage required to lift 4,590 total dynamic head feet? In this case, it's very simple. If you divide it 4,590 over 45, the head per stage, this will give you the minimum number of stage required to lift that well. At the same time, what will be the horsepower required to run this pump, required to stage? Because in order to sizing the motors, you have to calculate, the horsepower required to drive the motor, to drive all the bottom hole assembly, the pumps plus the parts below. But the main horsepower generated is from, required is from the pump itself. In this case, at that production, you need around 1.8 horsepower, just for each one of stage. Then, depend on the number of stage, what I calculating, if I multiply by 1.8, will give you the total horsepower required to run this pump. And this pump, if you look, it run at the peak efficiency, almost the peak efficiency. It's a little bit over 70% is the peak efficiency. This is just a very simple techniques, how you calculate the number of stage, the brake horsepower, or the horsepower required per stage, in the total number of stages, and the total required horsepower, and so on. The number of stage, based on that, as I said, 4,950 divided by 45, the number of stage, the head per stage, then I need at least 102 stage, and depend on the standard housing for each company and so on. Maybe you're not found exactly, this is housing is accommodated 102. Then I need to have housing at least accommodate that, or a little bit higher, couple of stage more than that, but not less, Then the housing, what I need to change, need to select, should be at least have 102, 103, 105, depend on the housing size and so on, Then pump load, as I mentioned before, the pump load here is a pump load, is a pump brake horsepower, it both hydraulic and mechanical horsepower. The total horsepower this required to drive this pump, The pump brake horsepower is increased and decreased with specific gravity of the fluid. Taking into consideration, when you're sizing the motors, is this well, currently as initially producing only oil, and with time will be a how much expecting the water cut will be, the water specific gravity and the oil specific gravity, then I have to consider when I start to sizing the motor or the brake horsepower here, when I need to to calculate it and so on. Then the pump load is equal, the brake horsepower for each stage multiplies the number of stage and, depend, as I said, in the specific gravity of the float. I have to consider the worst case, for example, this well, currently producing, clean oil, only oil with API 45 degree. But, I expected after 6 months, 1 year, something like that, water cut may be reached 25%, 50%. How much the specific gravity of the water is, and how much the specific gravity of the average specific gravity of the lifted fluid, and so on. After selecting the suitable pump intake of separator or not separator and seal and so on, I have to, to find out, what is the horsepower required just for each pump, for each of these bottom hole assembly part. And I added to the pump loads, calculated from the brake horsepower and so on. Then the total required motor load should be at least minimum equals, the pump loads, the brake horsepower for the pump, plus the intake, plus the seal, plus anything, can be added if you found, and so on, in order to run the motor, powerful enough motors to run all my system and so on. However, there is in the website, there is a very simple technique called 9 steps technique. If you want to just to understand the basic calculation, the basic design of the ESP system, you can go through this one, showing, step 1, what you need to do, step 2, what you need to do, step 3, 4, and 5, like collecting data and analyzing the data and analyzing the prediction, what will be happen for the wells, specific gravity now, water cut will increase, gas, what's going on, fluid level even, because, now I'm calculating this based on a dynamic fluid level, but what type of reservoir? Is it depletion drive reservoir or water drive? Depletion drive, that's mean with time the fluid level could be go down, because the static reservoir pressure was go down. This all that analysis. I collect the data and analyzing the data, this data will be, stable with time or expecting to change. What is expecting to change on that? Based on the well productivity, I have to determine, the production rate and the pump depths, I have to calculate after that, the fluid volume, including gas and pump. Remember, fluid volume at the pump. Fluid volume at the pump is different than the flow rates at the tank. You have to consider the shrinkage factors here. When you calculated the volume, the pump have to be displaced downhole, calculating the total dynamic head, select the pump, which can be at highest efficiency, optimizing all the component size of all the component, and with a prediction what could be changed for this well, I have to correct also or calculate, select the best type of cable, size of cables, and so on, as in the surface, what surface control I should have, what transformer I need to have, step up or step down, how much should be, volting, this transformer should be, changed, based on the pump and the wellhead and so on, all the other. This is just a very simple, and it's available on the website. If you go to 9-step ESP design, you can find this in details, these papers or these documents, it can support and can help you for that. It's just, brief about what we are not completed, based on last price. And now, it's open, for questions. If you have any question regarding ESP or any type of artificial lifts and so on.